Welcome to Chapter 7. Here we're going to be looking at sections 7.1 and 7.2, dealing with the concepts of eigenvalues and eigenvectors. So we're going to first establish the relationship, define what an eigenvalue and an eigenvector are, look at how to find them, and look at some of the additional properties that we see from them. So let A be an n by n, so a square matrix, if V is a non-zero vector in Rn and lambda is a scalar such that A times V equals lambda times V. So if we have a non-zero vector and a scalar for an n by n matrix such that the matrix times the vector equals the scalar times the vector, we call V an eigenvector with corresponding eigenvalue lambda. And sometimes you'll see these abbreviated, so a lot of times you'll see like E vector and E value if we're just using shorthand. So eigenvalues and eigenvectors produce this relationship. They come as a pair. So if we consider, for example, the matrix 2, 1, 3, 0 and the vector 1, 1, if we take A times V, so that's 2, 1, 3, 0 times 1, 1, that gives us, so we get 2 times 1 plus 1 times 1, so that's 3. And then 3 times 1 plus 0 times 1, so that's also 3. We get 3, 3. And look at how that's related to V. That's the same thing as 3 times 1, 1. And that is the lambda V relationship. So lambda equals 3 is an eigenvalue with corresponding eigenvector 1, 1. So this is the relationship between an eigenvalue and an eigenvector. Now, in order for us to find eigenvalues and their corresponding eigenvectors, we need to look at some logical equivalencies here that are going to help us kind of develop our process. So we know that lambda is an eigenvalue of A if and only if there exists a non-zero vector V with AV equals lambda V, right? That is the definition that we just established up top. Now, we're going to kind of go down the list of equivalencies here. So we know that if there exists a non-zero vector V with AV equals lambda V, we can go ahead and subtract this term over here, and then we can factor out that common vector of V. So what we would have left is A, not just minus lambda, but it would be A minus lambda I, where I is that identity matrix, times V equals 0, and that's the 0 vector. So again, if you took AV, subtract the lambda V over, equals 0, factor out the V from both, keep it on the right-hand side because of the matrix multiplication, it does matter. But then when you're done, lambda isn't just a scalar by itself. What you have is lambda times basically like this identity matrix for whatever size matrix you need, 2 by 2, 3 by 3, bigger, etc. So this is the relationship that we have now. This A minus lambda I, that is just a matrix because you're going to take basically lambdas, go down the main diagonal, subtract that away from A. So you're going to have a new matrix here times a vector equals 0. this system of equations that we've established here is how we define the null space. So we can say instead of there exists a non-zero vector v with this relationship, we can say there exists a non-zero vector v in the null space of A minus lambda I. So whatever that new matrix is, there is an element of the null space of that matrix that satisfies this relationship. If there exists a non-zero vector in the null space, that is sufficient to tell us that that matrix itself is not invertible. Right? This is still a square matrix. This is n by n, and I will also be n by n. So this is a square matrix, but the fact that there does exist a non-zero vector in its null space tells us that the matrix will not be invertible. If the matrix is not invertible, that means that the determinant of that matrix, A minus lambda I, must be equal to 0. So this gives us a nice, much more helpful test that says lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. So we can take the original matrix A, subtract off lambdas from the main diagonal, and then take that matrix, take its determinant, set it equal to 0, and use that to solve for the eigenvalues, solve for lambda. And of course, we're going to see examples going through this process exactly. Once we obtain the eigenvalues, so this is the process to find all of the lambdas. Once we find all of those, we solve the corresponding linear equations to find the eigenvectors. So basically, we're going to go back into that null space, right, that system of equations, plug in each lambda that we found, and then find its corresponding vector from the system. So let's take a look at an example. I think it gets a lot simpler once you actually see one done. So find the eigenvalues and eigenvectors for this matrix A. So we're going to take the determinant of A minus lambda I and set that equal to 0. So, and again, lambda I, in this case, this is a 2 by 2. So this is going to be, right, the identity matrix is this. But when we multiply by lambda, the main diagonal picks up lambdas, and everything else remains 0. So again, this process here is just subtracting lambdas off the main diagonal of A. So we're getting 1 minus lambda, -3, 1, and 5 minus lambda. And that determinant will be equal to 0. So this is our general setup. So this is A minus lambda I. Now we need to actually take the determinant. This is a 2 by 2, so we'll do AD minus BC. So that's going to be 1 minus lambda times 5 minus lambda minus 1 times -3 equals 0. And now we need to solve this for lambda. So basically we need to redistribute this so that we can combine this additional number and then try to refactor if possible. And again, this is pretty much how it's always going to go. So this gives us a lambda squared. We get +1 lambda minus 1 lambda minus 5 lambda. So that's -6 lambda plus 5 plus 3. So this is going to be +8 equals 0. This is factorable. We get lambda minus 2 and lambda minus 4. Right? That gives us -6 and then +8. This gives us two values. Lambda 1 is 2. Lambda 2 is 4. So we have two eigenvalues. And now we need to find the eigenvectors that correspond with them. So we're going to go lambda 1 is 2. So we'll do this one first. So we're looking at the null space of a minus lambda I. So this is a minus 2i in this case, which essentially is just telling us to subtract 2 off of the main diagonal instead of lambda. So we're taking the same matrix here, but we're replacing the lambdas with 2's. So 1 minus 2 is negative 1, negative 3, 1, and 5 minus 2 is 3. The null space of this matrix, that's the same thing as setting all the equations equal to 0. And you can see very quickly here that that second row is going to disappear. We've got the pivot right there. So y will be a free variable. X, if you subtract that over, gives us negative 3t. So our first eigenvector is going to be negative 3t and t. A lot of times with these eigenvectors, so the free variable is there, but oftentimes with the eigenvectors, we understand that the free variable is there and that it's any vector of this form. So a lot of times you will see these written without the free variables in them. So both of these represent the same thing. It's just with this one, we understand from context that it's any multiple of this vector, not just this one vector. But we often just take the eigenvector proper. Kind of we just take the main form of the vector and ignore the free variable just for the sake of notation. But both of these are equivalent. And we'll talk at the end of the problem kind of when to use which one. So lambda 2, so that was 4. So we're looking at the null space of a minus 4i. So we're subtracting 4 off of those main diagonal terms. So that's going to be negative 3, 1, and 1. So for our null space, so we get negative 3, 1, and 1, augmented with zeros. And of course, that gives us this matrix, which gives us y equals r, so another free variable, and x will be negative r. So v2 is negative r with r, or just negative 1 and 1. So notationally, when we're writing the final answers here, it's asking us for the eigenvalues and eigenvectors. We'll typically write them as a pair. So this would be lambda 1 equals 2. The textbook uses this notation, so they would put t there, and they would write it out just with our standard vector form. They don't necessarily write it as columns. And lambda 2 is 4, with v2 being r times negative 1, 1. This is again the This is the textbook notation. And that's perfectly fine. Sometimes the questions will ask, so if it asks for the Li eigenvectors or a basis for the eigenvectors, that would be a case where we could just write them as -3, 1, and -1, 1. So, and you'll see a lot of questions will ask us for the Li eigenvectors because a lot of them do have that free variable involved. Some of them will have multiple free variables, so you're splitting up into multiple vectors. But this would be kind of that general form as well. So this is another alternative. And of course, if you're looking for a basis, the free variable comes out every time. You can also see them written as eigenvalue, eigenvector pairs. You don't see this one quite as much, but you could also see, 2, -3, 1, and then 4, -1, 1, like that. So a lot of different ways of writing it. Technically speaking, they are vertical vectors. They're written like column vectors like this. But we have a general, again, understanding that if we write them like this, where they're in this kind of row vector form, we still understand that they would look like this. But a lot of times for the sake of writing it, especially in a textbook where they're typing everything, it's just easier for them to type it out like this. But they're equivalent. So it's the same thing. You're getting the same result either way. So these would be our eigenvalue and eigenvectors for this matrix. So 2 and 4 with their corresponding eigenvectors, -3, 1, and -1, 1. Now, for any given matrix A, we have this expression P of lambda is equal to the determinant of A minus lambda I. So the determinant of A minus lambda I, that's the calculation that we just did to find the eigenvalues. This notation, the P of lambda, is called the characteristic polynomial of A. The characteristic polynomial essentially just gives us that formula, the one that we have right here, for all of the eigenvalues. So in the previous example, P of lambda would be lambda minus 2 times lambda minus 4. So this would be the characteristic polynomial for this matrix. Characteristic polynomial, we'll look at more of the implications of it as we continue, but essentially it's just a quick way to identify the eigenvalues of the matrix, and also like how many times the eigenvalues show up, things like that we'll talk more about later in the sections. Let's take a look at a 3x3 example. So find the eigenvalues and eigenvectors for this 3x3 matrix. So we're going to take determinant of A minus lambda I. So we subtract lambdas off the main diagonal, and everything else stays the same. So we're going to get 3 minus lambda, a 0 and a 1, a 2 minus lambda in the middle there, a 0 and a -1, and a 2 minus lambda down here, the -1 and a 0. And we're going to set that equal to 0. Now, when it comes to solving out these equations, especially for 3x3s, the method that we use can vary from problem to problem. You have to think back to chapter 3 a little bit, how we compute determinants. You can use cofactor expansion. That's a pretty common way of doing that, especially with one like this, because you have this term here and all zeros in that first row. So it might be easier to just set it up that way. You can do like the traditional kind of cross product method, which is just, basically one case of a cofactor expansion. You can use like the arrow method. So going, the arrows down the diagonals and then the arrows up the diagonals as well. Or you can like use EROs and then try to manipulate it that way. So it's up to you how you want to compute the determinant. But for this one, again, since we have all zeros over here, using either cofactor expansion or like the quote-unquote kind of cross product method is the easiest one here. So we get 3 minus lambda times this little 2x2 subdeterminant here. So we're going to get AD minus BC for that. So that's going to be 2 minus lambda squared, because there's two of them, minus -1 times -1. So that's just -1 equals 0. And now from here, we'll get, this gives us lambda squared. And then we get a -2 lambda, a -2 lambda. So -4 lambda plus 4, but then a -1 right here makes it a +3. Okay, and let's not multiply this all together because we're trying to refactor and make this simpler again. So we get 3 minus lambda. This one does factor as lambda minus 3 and lambda minus 1 equals 0. Notice these two, if you were to take out a negative from this would give you lambda minus 3 also. So it would be the same thing as this one. So this gives us lambda equals 3, lambda equals 3, and lambda equals 1. So we had the lambda equals 3 show up twice, and that's okay. It doesn't change how we solve for its eigenvectors. So let's start with that one. Let's start with lambda equals 3. So we're doing the null space of A minus 3i. So we're going to subtract off 3 from the main diagonal. That's 0, 0, 0, 0, negative 1, negative 1, 1, negative 1, negative 1. Simple rearrangement here gives us 1, negative 1, negative 1, 0, 1, 1, 0, 0, 0. All augmented with zeros because it's the null space. So we get z will be a free variable t. X and y will both be in terms of that. So y will be negative t. X will be, that's negative negative t. So that's t minus t. So x is actually 0. So our first eigenvector, so let me label this, it's lambda 1, and v1 will be 0, negative t, t, or t times 0, negative 1, 1. And then lambda 2 is 1. So we're taking null space of A minus I, right, just one I. So we're subtracting 1 off of the main diagonal, so that's going to give us a 2, 1, and a 1. So 2, 0, 0, 0, 1, negative 1, 1, negative 1, 1. And this time, this one can cancel out this one. This row cancels out the rest of that row. This works out to 1, 0, 0, 0, 1, negative 1, and all zeros. So we get z is r, y is also r when you add that over, and x here is also 0. So our second eigenvector is 0, r, or r times 0, 1, 1. So our eigenvalue eigenvector pairs, so lambda 1 is 3, v1, again, I'll just use the Li eigenvector, 0, negative 1, 1, and lambda 2 is 1, v2 will be all vectors with the form 0, 1, 1. So we can notice here that that first eigenvalue, the 3, it appeared twice in this equation, but it still only produced one eigenvector, and that's okay. We're going to talk more about the implications of that and what exactly that means later on in this section, and then particularly in the next sections as well. But the number of times that the eigenvalue appears is called its multiplicity. So in this example here, we would say we have lambda equals 3 with multiplicity 2. That would be how we would describe that. And it can be shown that our characteristic polynomial can be factored as the following. P of lambda equals negative 1 to the n times lambda minus lambda 1 to the m1 times lambda minus lambda 2 to the m2, etc., all the way to lambda minus lambda k to the mk, where the lambda 1 through lambda k's are the distinct eigenvalues, and m1 through mk are the multiplicities. So instead of writing lambda minus 3 times lambda minus 3, we would just put lambda minus 3 squared, right? Eigenvalue of 3, multiplicity of 2. So this does give us more information about the characteristic polynomial. The characteristic polynomial does give us multiplicity as well. And again, if we look back at this previous example, we had this right here. So we had, when you pull this one around, so you factor out the negative, you get a lambda minus 3 times a lambda minus 3. So that's lambda minus 3 squared, and then lambda minus 1 is still there. So the characteristic polynomial for this last example was P of lambda equals negative lambda minus 3 squared times lambda minus 1. Now, let's get back to this idea of this eigenvalue having a multiplicity of 2, but only producing one eigenvector, right? One Li eigenvector. We have some terminology to go along with this idea. So if we have an n by n matrix with n Li eigenvectors, so if it's a 2 by 2 and we have 2 eigenvectors, or a 3 by 3 with 3 eigenvectors, etc., then the matrix is called non-defective. Otherwise, it is defective. So the way that we describe this is that each eigenvector needs to pull its weight. So if the number of Li eigenvectors associated with lambda is less than the multiplicity of lambda, this would make the matrix defective. Okay, so in other words, if we have an eigenvalue with a multiplicity of 3, for example, then it better produce 3 Li eigenvectors to go along with it. Or like in this last example, we had an eigenvalue that had a multiplicity of 2, but it only produced 1 eigenvector. It needs to produce 2 as well in order for this matrix to be non-defective. So in this previous example, A is defective, because we had a 3 by 3 matrix that only had 2 Li eigenvectors. So this matrix did not have enough eigenvectors to be non-defective. So it is defective for that example. And again, we'll look more in the future sections about the implications of what it means to be defective versus non-defective. But for right now, this is kind of where we're at. Each eigenvalue needs to pull its own weight. That says eigenvector, doesn't it? That should say eigenvalue. Each eigenvalue needs to pull its own weight. So, moving forward, another piece of terminology for us to take note of, that null space of that square matrix A minus lambda I, because this comes up so frequently, we don't call it the null space of A minus lambda I anymore. We call this an eigenspace. An eigenspace. An eigenspace is just a null space of specifically A minus lambda I matrix. The notation we use for this is E sub lambda. So let's take a look at an example. Given this matrix B, find the characteristic polynomial, find any eigenspaces of B, and then determine if B is defective or non-defective. So we've got a few things going on here. First things first, we need to get determinant of B minus lambda I. So we're going to get a 2 minus lambda, a 3 minus lambda, and a 3 minus lambda. Set equal to 0. Again, a cofactor expansion is probably in order here because you've got a column with all zeros except the first one. So we get a 2 minus lambda times that 2 by 2. So that's 3 minus lambda squared minus 1 equals 0. So we get 2 minus lambda. This gives us lambda squared minus 6 lambda plus 9 minus 1, so that's plus 8. So that's lambda minus 2 and lambda minus 4. So we get lambda 1 is 2 with a multiplicity of 2, and lambda 2 will be 4. Now, this poses the possibility of a defective matrix. That doesn't guarantee it. We're going to need to check this. But if there was only 3 unique values, if we got like 2, 4, and 5 or something like that, each of these eigenvalues will produce one eigenvector. We don't have to worry about it not producing any. It will produce one. The question is, does this one produce 2? Okay, that's the real question. So if all of these, if we had just gotten like 3 distinct eigenvalues, we could automatically say non-defective because there are no multiplicities greater than 1, but that's not the case here. So the characteristic polynomial, so we'll start with that. So characteristic polynomial P of lambda, we've got, so it's -1 to the n, which n is 3, or you can just picture factoring out the -1 from here again. That's negative lambda minus 2 squared times lambda minus 4. So that's our characteristic polynomial. Now to determine the eigenspaces and defective or non-defective, we're going to start looking here. So we have null space of b minus 2i. So we're going to subtract 2 off of those main diagonal terms. So that's 0, negative 5, 5, 0, 1, negative 1, 0, negative 1, 1. You can probably see how this is going to work out. We're going to get 0, 1, negative 1, and then 0 rows down below. So we get z will be t, y minus t is 0, so y is also t, and x, don't be fooled, x is not necessarily 0. This means that x does not show up in this system, which means it can be anything. That makes it free. So x will be another free variable, r. So our eigenspace for lambda equals 2. Okay, so this is, you don't have to write lambda equals 2 here, but just I want to be clear because I called this lambda 1, but this is based off of what the actual number is. So this is E2 is going to be the set of vectors RTT, which would be the span of, if we bust out the variables, that would be 1, 0, 0 for the R and 0, 1, 1 for the T. So that would be E2 would just be vectors of this form or the span of these two. If we wanted like a basis for E2, a lot of times we'll just take the basis for it, which allows us to just drop the span notation. So that's 1, 0, 0, 0, 1, 1. So this would be the basis for the eigenspace that corresponds to lambda equals 2. And if we look at the other eigenvalue, so that's null space of, that's b minus 4i. So we're subtracting off 4 from those main diagonal terms. That's going to be -2, -1, and -1. And everything else will stay the same. So this will give us, so we'll get a 2 here, a 5 and a negative 5. We'll get a 0, 1, 1 here, and then an all 0 row at the bottom. I didn't solve this for perfectly row echelon form, right? It's 2 instead of 1. But ultimately, we're just solving for the relationship of the free variables, so it's not going to be that big of a deal. So z will be t, y will be negative t, and 2x minus 5t minus 5t equals 0. So that's 2x minus 10t. Add the 10t over, divide by 2. We end up x equals 5t. So we got the relationship either way. So E4 is the set with vectors 5t, negative t, and t. So our basis for E4 is 5, negative 1, 1. And again, it didn't ask us specifically for the basis, but a lot of times we will. We like to, again, just write those Li eigenvectors. So we'll kind of bust out the variables and write the corresponding eigenvector that goes along without the free variable there attached to it. So those are the eigenspaces. And the final question, defective or non-defective, we actually could have answered that back here with lambda equals 2 because that eigenvalue had a multiplicity of 2. It needed to produce 2 Li eigenvectors, and it did. So that eigenvalue pulled its weight. Okay, so it did produce 2 Li eigenvectors, and then, of course, lambda equals 4 produced 1. So they have 3 eigenvectors for a 3 by 3 matrix. So 3 Li eigenvectors. Thus, B is non-defective. All right. Now, if we take a look at the top of the next page, we're going to work with something here that's a little bit different, something that you're probably not used to working with in your previous math classes. We're going to work just a tiny bit with complex numbers. So complex numbers, imaginary numbers, there are entire fields of study on these topics for calculus and linear algebra, differential equations, all of those things that involve complex numbers. We're only going to be scratching the surface of complex numbers in this course because, again, that's not our primary focus, but they do play a role in this process. So if A has a complex eigenvalue, so that's A plus BI for lambda, the corresponding eigenvector, if A has a complex eigenvalue that corresponds to an eigenvector V, then the complement A minus BI is also an eigenvalue with corresponding eigenvector V bar. So this is lambda bar and V bar. But it just means you're taking the complex conjugate of that value. So if it's A plus BI, this one's A minus BI. And then whatever that eigenvector was, we'll take its conjugate as well. So this is helpful because we know that these will always come as a pair with each other. If we take a look at this 2 by 2 matrix here, we get determinant 2 minus lambda, negative 13, 1, and 6 minus lambda. Set it equal to 0. 2 by 2, so we get 2 minus lambda times 6 minus lambda minus negative 13, so plus 13 equals 0. So we get lambda squared minus 6 minus 2, so that's minus 8 lambda, plus 12 plus 13 is plus 25, equals 0. And we would hope that it's factorable, but in this case it's not. This one is not factorable as is. So we need to solve using either the method of completing the square or the quadratic formula. Quadratic formula, I think, is a little more straightforward. So we get x equals negative b plus or minus the square root of b squared minus 4ac, so that's 4 times 25, all over 2a, so just 2. So that's 8 plus or minus square root of negative 36 all over 2. So that's going to give us, right, 6i right there. So divide everything by 2, we get 4 plus or minus 3i. So those are going to be our eigenvalues, the 4 plus 3i and the 4 minus 3i. So if we take lambda 1 to be 4 plus 3i, we're looking for the null space of this matrix subtracting off 4 plus 3i. So we get 2 minus 4, so negative 2 minus 3i, because it's being subtracted. Down here, we get 2 minus 3i. And then these stay the same, negative 13 and 1. We can perform EROs on this. I is an imaginary number, but it still behaves like a number. So if we go ahead and just permute the rows, let's get the pivot in that upper left-hand corner here. We get negative 2 minus 3i and negative 13, augmented with zeros. And then we just add first to second times the opposite of that, so 2 plus 3i times 1. So we get 1, 2 minus 3i. That one gives us 0. And this one, if you're worried that's going to make this one more complicated, it actually doesn't, because if you multiply these two together, these are complex conjugates already. So we get 4 minus 12i plus 12i, which cancel, and then minus 9i squared. I squared is negative 1. So you get 4 plus 9, which is 13. So basically we're taking 13 plus negative 13, so it actually gives us another 0. So it works out very well, very nicely for us. So we get here y will be a free variable t, x is x plus 2 minus 3i all times t. So if we subtract that over, we get negative 2 plus 3i times t. So our eigenspace for 4 plus 3i is going to be the set of vectors. If we get rid of the multiples of t, we get negative 2 plus 3i and 1. So that's our eigenspace, right? Our corresponding eigenvector for this eigenvalue. And the nice thing about the complex numbers is when you take the conjugate, the eigenvector also conjugates. So instead of negative 2 plus 3i, it's going to be negative 2 minus 3i and 1. So we actually don't even need to work with the second eigenvalue. We know that it will produce that complex conjugate in that first component. Now, the nice thing about working with the 2x2s when it comes to the complex eigenvalues and eigenvectors, and that's this note down here at the bottom of the page. We know that the matrix A minus lambda I is always not invertible. So there will always be, if you're talking about a 2x2 matrix, because the matrix is always not invertible, there will always be a row of zeros at the bottom. So like back up here, if we're looking for the null space of this matrix, we know that because this matrix is not invertible, we know that there will be a row of zeros at the bottom. So what this means in a 2x2 is we can simply eliminate a row. So like with this one, if I wanted the pivot to be up here, I could still switch these, but then we could just eliminate this row because we know that it'll turn to all zeros. Now, we algebraically showed that it turns to all zeros, but again, that property comes from the non-invertibility of the matrix. So that works out very much in our favor. However, we have to be careful. This does not work for 3x3 matrices or larger. This is only a unique property of 2x2s. As soon as you throw a third row into the mix, they can behave a little differently and still be not invertible. But again, for the 2x2s, it's a handy trick when working with complex because that means you don't even really need to worry about this ERO here or how that affects this number down here because we know it's going to turn into a 0. Again, as long as it's in 2x2. So that is just a brief introduction into complex eigenvalues and eigenvectors. But that brings us to the end of sections 7.1 and 7.2, introducing the idea of an eigenvalue, an eigenvector, an eigenspace, the idea of a defective versus non-defective matrix, and characteristic polynomials, multiplicities, all that kind of stuff. So we will be back soon with section 7.3.